representing a probability distribution. When I actually give capital letters I'm using here to represent variables, this is a probability distribution. This is really represents a set of probabilities in which X and W are assigned to the various patterns of X and W. So, for example, this right here, this conditional probability distribution, and this conditional probability distribution, what I'm really indicating here by this summary statement is simply that for all possible assignments of Y, W, and X, it is the case that the probability of an assignment to the variable Y conditioned on a particular assignment of W and X is simply going to equal the probability of that assignment to Y and that assignment to W, disregarding the assignment to X. And so this is just shorthand that I'll use and the book uses, but this is really when variables here rather than particular values are shown. It represents a probability distribution or a set of probabilities, each with a particular assignment. And you'll notice because of this conditional independence relationship, for every 2 probabilities, because these are binary valued variables, for every 2 probabilities in the situation where we're not assuming conditional independence, so this is one probability, this is a distinct probability in which the X values are different, we're really going to replace that by a single probability. Because the X assignment is not important anymore because of this conditional independence assumption. And every time I get rid of a single binary value, a binary valued variable from the conditioning side, I eliminate the number of probabilities I have to store by a factor of 2. And if I eliminate more probabilities, or more variables, rather, I eliminate still greater number of the need to store probabilities. So here is a Bayesian network, which is intended to represent the situation in the quiz. And you've done the reading, and so you know a Bayesian network is just a graphical representation of a joint probability distribution. And in this case, this represents the fact that Y is conditionally independent of, in this case, X, all its non-descendants, all of Y's non-descendants. Y is conditionally independent of all its non-descendants, given that the value of W has been assigned, its parent. And so this is the general statement for the semantics of a Bayesian network. Each variable or node is conditionally independent of its non-descendants given its parents, given this, each of its parents have been assigned to a particular value. So in this particular example, W and X are independent. Y is conditionally independent of all its non-descendants, or X, given that its parent has been, a single parent has been assigned to a value. Y is still statistically related to Z, so we don't say it's independent of its descendants. It's only its non-descendants that assignment of the parent will render conditional independence. Here I've simply put in light font probabilities that we don't actually have to store because we can compute each of these. The probability of not Y given W is simply going to equal 1 minus the probability of Y given W. Make sure you understand that that relationship, that I can compute the probability of not Y conditioned on W given the probability of Y conditioned on W. Don't be confused and verify that you understand that I cannot compute this given I know that. So we go through and look at the general case of space savings due to belief networks and more generally independencies. Nice example is given in illustration is given in this text. Again, assuming that all the variables are Boolean and I have n Boolean variables, that would indicate that I would have to, in general, store 2 to the n, actually 2 to the n minus 1, because I don't have to store that very last one. I can compute that given the sum of the others. But let's just say 2 to the n joint probabilities need to be stored for n variables, because there's 2 to the n different patterns of assignment to those n variables. But let's say that each of those variables is only directly influenced, or it's only has k parents in a Bayesian network representing the situation. Then each probability table will have at most 2 to the k assignments, joint probabilities based on, they're going to be conditional probabilities, the probability of each value assignment of the node given the patterns, possible 2 to the k patterns that condition that. And so the complete network for all n nodes or variables, we're going to assign 2 to the k numbers per each of those nodes, because again, each node has k parents, and so 2 to the k conditioning patterns for its probability tables. So if n, the total number of nodes or variables, is 30, and k, the maximum number of parents of each node, is 5, then for the Bayesian network, or taking advantage of conditional independencies, whether I use Bayesian networks or not, is going to require 960 probability assignments, and that's going to be compared to 2 to the 30th if I was going to explicitly represent the full joint distribution. That's going to be over 1 billion numbers. So in general, for something realistic, and n, 30 variables nowadays is very small, I can get a big savings if I can identify conditional independencies in the data. So here's an example of a Bayesian network that's due to Judea Pearl. I show him, he's more or less a co-inventor of Bayesian networks. Some would say the sole inventor of belief networks, but he's done some really groundbreaking work in graphical representations of probabilistic information. And so here's the Bayesian network that is due to Pearl. We're assuming that maybe this is in California, but you know, we have a fault line not that far from us out in the Mississippi River, so maybe this would apply to us as well one day. Hopefully you'll have graduated and gone other places in the country. But we've got an alarm system, perhaps 2 people living in an apartment complex. There are a couple things that can trigger this alarm. One is a burglary. Perhaps the alarm is explicitly designed for burglaries. But the other is an earthquake, which could also set off the alarm. Perhaps not the intended reason the alarm would go off, but nonetheless a reason that would cause it to go off. Either of these, whether there's a burglary and whether there's an earthquake, are almost certainly independent of each other. You might say that if an earthquake does happen and a burglary is in progress or about to be in progress, the burglar is probably going to call it off. But let's say, for the sake of argument, that they are truly independent events, because that situation where they simultaneously occur is so rare that, as the knowledge engineers for this, we decide it is not worth representing a dependency between burglary and earthquakes. So although one might exist, the conditions under which there would be an influence, and perhaps a negligible influence at that, would be so rare that I just don't worry about representing it. So either burglaries or earthquakes can trigger alarms. Again, these are independent variables, but the alarm can be set off by either one. So its probability distribution, the probability distribution of an alarm, would almost certainly depend on both of these conditions. And notice I'm just showing the positive values of when an alarm goes off. There'd be corresponding negative values. No alarm given this pattern, no alarm given each of those patterns. In this case, note that I'm not representing other information that might affect the alarm. I'm not representing information about if it's a battery-powered alarm or even if it's plugged into the electrical grid. I'm not representing the state of the electrical grid, although clearly that would have a impact on the alarm. That information is probably represented and probably captured in these probability tables. That is the probability of an alarm given both a burglary and an earthquake. Again, an extremely rare event. So let's just take a look at the probability of an alarm given a burglary and no earthquake is hopefully very close to 1 for a properly operating alarm. In fact, it's hopefully 1. But there may be some other conditions that would affect that probability that we're not representing explicitly. So we're not representing the state of the battery. And so the assumption is that the state of the battery and these other features that are relevant to whether the alarm goes off, while they're not explicitly represented, are still reflected somehow in that probability. The probability the alarm will go off given a burglary is close to 1 but not 1, because it's possible the alarm is faulty for some reason, or it's possible the power is down, a number of other things. And if an earthquake, this probability, the probability of not alarm given an earthquake might be considerably higher than we would think, because we might knock out electricity if we were feeding off the electricity grid rather than a battery. So it really depends. Then there's a couple of variables as to whether John calls in the situation or Mary calls in the situation. Again, if it's a burglary, primarily designed as a burglary alarm, we would intend these to be calls to the police or emergency units. But in this case, whether John calls and whether Mary calls, these are independent. They don't live together. The probabilities and inclinations to call are probably different, so they each have their own probability distribution associated with them. But these are conditioned only on the alarm. So if we know the alarm goes off, Mary will call independent of what caused that alarm. You might say these are not entirely necessarily reasonable. Some would argue that we should have a link from earthquake to Mary calls, because if an earthquake goes off, maybe somebody will call it in, but there's probably no need to notify anybody if an earthquake is called, right? I mean, people, and you would assume people know. And so arguably this is, we might have a link from earthquake to Mary calls, and that would be perfectly fine in terms of the topology of this network. There's nothing wrong with the parent of a, the grandparent of a node also pointing to that node as well as its parent. But we can simply argue that this is a reasonable network, and for whatever reason the knowledge modelers are not worried about that negligible situation in which an earthquake might occur. You know, why wouldn't John and Mary always call? Well, one, possibly they're lazy or ignorant. They may not be home. They might not know the alarm is going off. The music may be too loud, so they don't hear the alarm, or they simply may be ignoring it and assuming that somebody else will call. And arguably, that assumption that someone else would call, you know, John may know Mary and may know that Mary always calls, or vice versa. So there might be an argument in representing this domain that there be a link there. But we've decided not to represent it. So this is just a very simple network, and somebody who's designing this network has to make some choices as to what knowledge to represent, what perhaps modest or mild dependencies to overlook and not represent explicitly, because it just requires too much precision. You know, knowledge modelers are pretty good about determining the topology of a network. They may or may not be good in different settings for actually assigning probabilities. Fortunately, we can get the probabilities from data, and we'll talk about that. So let's go back and look at the original situation. You've seen this slide before, or one very much like it. This is the chain rule, but more importantly, we've got an ordering on variables. And this ordering is V1 followed by V2 followed by V3, V4, V5. There are alternative ways to order the variables that give you an equivalent, in the general case, an equivalent expression. This expression would compute the same value as that expression. They would both compute the joint probability of V1 through V5, joint probability distribution of V1 through V5. But this ordering is V4 followed by V2, followed by V3, followed by V1, followed by V5. So just remember many possible different orderings, and the importance of that is the algorithm for constructing a Bayesian network depends on a precise ordering. We assume a particular ordering of the variables over which we want to construct the Bayesian network or belief network. And so I'm going to assume V1, V2, V3, V4, V5 in constructing this network. So you take the first variable in the ordering, and it automatically becomes a root of the belief network that you're growing. At this point, you may or may not be able to assign probability values to the various values of that node, but you always select the first node in the ordering as the root. The second variable in the ordering is V2. And there are two possibilities here. In this example, V2 can become a child of V1 because, in fact, there is a probabilistic or statistical dependency between V2 and V1. Or V2 can become a new root, an additional node with no parents. And the algorithm for constructing the network would consider both those possibilities. The first possibility it would consider is V2 independent of V1. And if a judgment of independence is made by the person constructing the network or from data by the algorithm constructing the network, and we'll talk about the data approach in a moment, if there's a determination that these two variables are independent, then V2 simply becomes a separate node, a separate root. It has no parents. And so I'm just claiming this is true as the domain expert in this artificial example. And V2 is an additional root. And then we take V3. This is the third variable in the ordering. And again, the question we're going to ask is V3 independent of a subset of its predecessors Let's pretend that subset is V2, conditioned on a disjoint subset of predecessors, in this case V1. So in other words, does knowledge of V1 induce a conditional independence of V3 and V2? And if it does, if knowing V1 is all you need to know to predict, or I should put this another way, the probability of V3 given both V1 and V2, V2 is a variable that adds no additional information to this prediction of V3 if I already know V1. So the claim is that for all possible value assignments of V3, V2, V1, I don't really, this probability will equal this corresponding probability without reference to V2. And so this is a conditional independence. V3 is conditionally independent of V2 given V1, and so V3 is made a child of V1 and not V2. Yeah. And of course it goes away. I don't even see it when we're in slideshow mode. Okay. Again, there's nothing magical about this. I'm claiming that this is true about this environment, whatever that environment is. And now the next variable in the ordering is V4, and I'm assuming that V4 is conditionally independent of V1 given V2 and V3. So given V2 and V3, that's the second set here, V2, V3, and V1 in this case is in this first set. It is rendered unnecessary if I know V2 and V3. It adds no additional information. So in this case, I would make V4 a child of V3 and V2. And then again, assign the various probabilities. And finally, V5 is the last ordering here. And again, given either knowledge or data about this domain, the claim is made that V5 is conditionally independent of V1, V2, and V4 given V3. So given this relationship and the claim that that's true, then V5 is only a child of V3. So this would be the final Bayesian network under the assumptions that I've given. This right here, oops, one thing that I can't do here is there could be, when we go back and we evaluate these subsets, there may be more than one way of identifying subsets of predecessors that are not necessary conditioned on predecessors that you've actually looked at already that are necessary. So there might be a choice. I could have chosen to make V5 simply a child of V3 because of this, but it may be the case that there are some other conditional independencies that are true, and I could have equally made V3 a child of V1, and I can't even read it. What is that, V4? Yeah, V4 in this network. And that would have been another option. And so I choose one of those options. So the semantics of the graphical component again are that a node, say V3, is independent of all its non-descendants. It's independent in this case of V2 if V1 is fixed. It's still dependent on is still conditionally dependent on V5 and V4 because those are descendants of this node. I'm going to add another, before I post the slides, another slide concerned with conditional independencies that are induced by what are called Markov blankets. The book mentions those, but never explains them. So the Markov blanket of a node is, this is not the greatest example to illustrate it with, or maybe it is. The Markov blanket of a node, let's say V3, is all its parents, all its children, and all the other parents of its children. Okay, so every node in this graph would be in the Markov blanket of V3. So if there was a V sub 0 up here, that would not be included in the Markov blanket. If there were, say, descendants of V4, those would not be in the Markov blanket. If there were parents of V2, those would not be in the Markov blanket of V3. But what's interesting about the Markov blanket is it completely surrounds a node, and the reasons the parent of the children are important is somewhat subtle. I'm not going to get to that. But if all the Markov blanket variables of a node are fixed, then that node is conditionally independent of every other non-Markov blanket node in the network, whether it's a descendant or not. Okay? You know, there might be, I might ask something about the Markov blanket later. Again, I'll add a slide to this deck before I post it. It's important for some reasons. So any order of the variables, you can use any order, as I said already when I took a look at this example of building this abstract Bayesian network. Any order of the variables will lead to a correct Bayesian network. But different orderings of the variables will lead to potentially Bayesian networks of different complexity, different numbers of nodes, or not different numbers of nodes, because a variable corresponds to a node, and the number of variables isn't going to change, but the number of links between the nodes, number of arcs between the nodes, and thus the number of probabilities that you'll actually have to store can change as a result of the order. So this belief network might have been constructed with this order of variables: burglary, earthquake, alarm, John calls, Mary calls. This Bayesian network is consistent with other orders too. This Bayesian network topology is consistent with earthquake followed by burglary, followed by alarm, followed by Mary calls, followed by John calls. We would expect the same network in that case. But there are other orderings, like this one, burglary followed by earthquake, followed by alarm, followed by John calls, followed by Mary calls, that might lead to a significantly different network. So let's see. Oh, okay. So yeah, these are the probabilities and the conditional independencies that I use to construct this network. If we go to another ordering, different from the one that we used to build the first one, let's say we looked at the ordering John calls, Mary calls, earthquake, alarm, burglary. Let's say that was the order in which we considered the variables. And remember that in this case, there are 4 arcs in the Bayesian network. In this case, we might start with John calls. That's here. And so that is made a root with some probabilities. Some of these probabilities may be extremely hard to estimate for an expert, although a data approach might be able to estimate them from large amounts of data. And the next variable we consider is Mary calls. Now, well, if we know that John has called, this is going to raise the posterior probability, the assessed perceived probability that the alarm has gone off. Okay? But we can't link. When we consider Mary calls, we've not yet considered alarm. And so the only way of representing any information about whether the alarm has gone off, and John's call is evidence that the alarm has gone off, and we know that because we know about the domain, is that John is called. And so John calling has got to be, if we want to capture that information, has got to be a parent of Mary calls. Okay, these are not independent any longer, or conditionally independent. If John calls, the probability of the conditional probability of an alarm is increased, and if the conditional probability of an alarm is increased based on the available evidence, then the likelihood that Mary is going to call has gone up as well. The next variable we might consider is earthquake. In this case, earthquake is, in thinking about this domain, is potentially a more likely reason for both John and Mary calling. And so in thinking about how John alone might call, Mary alone might call, each of those calls is going to add additional evidence that something has gone wrong. And that going wrong, because we haven't considered burglary, the perceived possibility of an earthquake is going to go up as a result of 2 calls or even 1 call. But because the perceived probability of an earthquake, or for that matter a burglary, either reason at this point would induce the same kind of result, both John calls and Mary calls would likely be parents of earthquake, 2 parents. If an earthquake has gone off, or if there has been an earthquake and the alarm is going off, this alarm is perhaps the next thing we would consider. Again, if we were to assess these probabilities, the probability of the alarm given an earthquake alone is some value. The probability of an earthquake, of the alarm going off, given that there has been an earthquake and both John and Mary have called, are going to be increased still more. That would be the argument here. And so just reasoning about this domain, we might conclude that all these variables should be parents, all the predecessors should be parents of alarm. And what we're saying there is the probability of an alarm given an earthquake has its value, but the probability of an alarm given an earthquake and John calls goes up, and the probability of an alarm given an earthquake and John calls and Mary calls still goes up more perceptibly, enough to perhaps pass a statistical test. And so we would make all of these parents, all 3 variables, the parents of alarm. We might then add burglary, but I'm not going to at this point because this network is already more complicated than the earlier network. This has 6 arcs versus the complete network earlier that has 4. And with these, with this node right here, for each of the alarm values here, or for say positive alarm values, we would have 2 to the 3rd or 8 patterns associated with these binary values, or binary valued variables. So we would have 8 values here, or 8 probabilities here, from which we can compute another 8 for the probability of not alarm given those patterns, that we would have to store, which would be considerably more than in the table for alarm in the earlier example, in which we simply had to store 4 instead of 8. So in general, ordering, different orderings give you different networks. Some are going to be more complicated than others. As a general rule of thumb, it's the case that if you order the variables from those that correspond to causes to those that correspond to manifestations, that leads to easier, simpler networks. That is because the causes induce conditional independency on the manifestations. If I tell you that I have the flu, there are certain symptoms associated with the flu, and knowing that I have a flu might render those various symptoms conditionally independent of each other given knowledge that, that I have a flu stake or I don't have a flu. Where does knowledge about conditional independencies come from? Well, one place it comes from or can come from is data. And this is an example you've seen before in the context of one of the machine learning lectures, the naive Bayesian classifier lecture from a couple weeks ago. Congressional voting records are always fun to look at. And by the way, any sociologists here? So anyone know Professor Hess? No one? Okay. So he's a sociologist. He's an environmental sociologist, and he analyzes congressional voting records as part of his research to look to see how members of Congress vote on various environmental issues. So if you're interested in that kind of thing, you can go talk to him. But here, we have a number of variables: party, immigration, Star Wars, and I've introduced this data set to some extent. This is to some extent outdated. I mean, the parties are pretty much the same from the 80s. Immigration is still a hot issue. Star Wars, missile defense system, not so much, but still defense issues, I suppose. So a lot of these are still relevant today, and they were a long time ago too. But let's consider constructing a Bayesian network. And in this case, we actually have data available. We have data on the voting records for the various members of, in this case, the House of Representatives. If this is the ordering, and I'm following this rule of going from the causal variables, and party is causal of the way people vote. If you know anything about the way the U.S. House works, you've got the whip there who is whipping up support for the party's causes. So party really is causal, and that takes into account the prior beliefs of why people identify with party, but ordered in a certain way, and certainly party is the first one or causal one. So that's selected as the root. Again, I just have to store one probability. This is old data, so 52% back in the day were Republican, and 48% were Democrat. So I would have probabilities associated with these based on the data, based on proportions that estimate probabilities, or are in fact exact probabilities over this data. And the next thing I consider now is immigration, and I want to consider whether immigration is independent of party. And again, in talking about the naive Bayesian classifier, to some extent we've talked about this already. We take a look, one way we can do it is we can use a statistical test, and we can take a look at what the actual cell values within a matrix representation of votes. Here's party, here's the votes on immigration for whatever bill this was. And these are the actual counts. 17 Republicans actually voted yes on this immigration bill. 209 voted no, 160 Democrats voted yes, 49 voted no. So these are the actual counts. And these are the counts that you would expect if party and immigration were independent of each other. So how were these predicted counts computed? You make an assumption of independence between party and immigration, and you take, if you want to know the joint predicted probability of a yes vote by a Republican, it's the probability of Republican times the probability of yes times 435. And so that is, under the independence of independence, this is the number of yes votes by Republicans you would expect. This is the number of no votes by Republicans. And you do the same for Democrats. And so this is a predicted matrix of counts, and this is the actual matrix of counts. And then a statistical test like chi-squared is concerned with saying, are these counts, are the actual counts close enough to the predicted counts to conclude that with some high confidence level, these are independent variables. In this case, the answer is probably no. These are radically different cell counts for these two matrices. And so the conclusion would be that we cannot conclude independence with high degree. And for purposes of machine learning system, we're just going to conclude that they're dependent. And that means that we're going to make immigration a child of party, in this case, because we could not establish a good argument for the independence of immigration and party. And the next variable in this ordering that we're considering is Star Wars, and we're going to consider it in a certain order. Star Wars independent of party and immigration. And that is the probability of Star Wars given both party and immigration equal to or approximately equal to the probability of Star Wars by alone. If yes, then we're going to stop and make Star Wars the root or an additional root. Otherwise, this order could be swapped. It doesn't matter, but is Star Wars independent of immigration conditioned on party? If yes, then stop and make Star Wars a child of party. If no, then ask the same issue about whether Star Wars was independent of party conditioned on immigration, and continue in that way, looking at the different subsets of the variables that you considered earlier. In this case, there's a very limited number. And in this case, the first thing is we might ask, is Star Wars independent of party and immigration? We might look at the conjunction, immigration, party, and then look at the projected cell counts for Star Wars within these predicted counts, if Star Wars was in fact independent of the conjunction of party and immigration. But these are the actual counts. And they're different enough that we might conclude not independent. And so in that case, we would make Star Wars a child of, after an initial couple of steps, make Star Wars a child of party. The idea is that Star Wars is conditionally independent of immigration given party. Is Star Wars independent of immigration? If I hide this node and I ask you, Star Wars independent of immigration? I would say no. Because if I know that somebody voted yes on Star Wars, I can tell you with high probability that I'm probably right, they voted no on immigration. Okay? And that's just from the data. The probability of Star Wars, again, this party you could think of as kind of a hidden variable relative to this, but there is a statistical relationship between Star Wars and immigration. So the claim here, the claim of this network is not that Star Wars is all by itself independent of immigration, because they're not. They're highly correlated, inversely correlated in this case. A yes vote there probably means a no vote there, and vice versa. Strong statistical correlation. But Star Wars is conditionally independent of immigration given party. That is, if I know the party, I can tell you with high confidence what the vote on Star Wars is, and knowing the party, I can tell you with high confidence that I can tell you what the immigration vote is. Now, this is probably not exactly right, okay? There might be an argument for drawing a link between these two because there are different kinds of Democrats, there are different kinds of conservatives. There are liberal Republicans and there are conservative Democrats. And if you were interested in looking at those subpopulations and you were thinking about those subpopulations might be sizable enough that you would not make a conclusion of independence conditioned on party. It still wouldn't be enough. Somebody could still say, Republican but voted no on Star Wars. And that might be correlated with a yes vote on immigration, because given only those two issues, we might be talking about a liberal Republican or a conservative Democrat, something like that. And so, you know, these relationships, again, may be approximate, whether you're using a data-driven approach or whether using an expert approach. So this process that we are going through, we haven't gone very far, but this is an important form of what is called unsupervised machine learning. And even though we have this party affiliation here, there's nothing about this, as we'll see in a moment, there's nothing about this Bayesian network that we're building that is focused exclusively on predicting party. In supervised learning, we would be building something that was focused exclusively on predicting party, if in fact we were building a classifier for predicting party. But when we're done with this Bayesian network, we'll be able to predict the likelihood of Star Wars votes, yes, immigration votes, no, and any other issue here, as well as party. So it's unsupervised. There is no variable we're setting aside and saying, we're only going to be predicting this. In a Bayesian network, you can predict any variable given other variables. So that's an important characteristic of unsupervised machine learning. So this is really the third machine learning method that you've learned about. The first two were supervised, naive Bayesian classifier and decision trees. Now, in this particular example, we've only gotten so far in it. You can view this as supporting a naive Bayesian classifier. But when we did naive Bayesian classification, we made the assumption up front that the variables were conditionally independent of the classification, the classifying attribute. We made an assumption up front that immigration was independent of Star Wars given party, and immigration was independent of the crime bill given party. We made those assumptions. We're not making those assumptions here a priori. Any result that we're coming, conclusion that we're coming to about conditional independency is derived from the data exclusively in an unsupervised method. So this isn't, this is related to but different from this technique of naive Bayesian classification. But a network like this can be used to support naive Bayesian classification because it makes the important assumptions. Here, if we know that somebody did not vote yes, or somebody voted yes on immigration and somebody voted no on Star Wars, we would want to predict the party. Again, we can represent that as this as a conditional independence, a conditional probability of Democrat given these votes, and a conditional probability of Republican given these votes. And I can go through and I can compute which the highest is. And the information I'll need is in these probability tables here because of that conditional independence. So we might come back and talk about this later before the second exam. The naive Bayesian classifier makes an assumption that this is the structure where the attribute you want to predict is at the root, and all the variables that you might use to predict it are conditionally independent of each other and are all immediate children of the root. But we attained this by simply looking at the data and making judgments. We're just, this is the second place that, at least the second place where knowledge of conditional independence might come from. It might come from what I would just call first principles. We reason about